Hello everybody and welcome to day 2 here at the OHBM Open Science Room. We're very pleased to welcome you and to welcome our audience joining from the OHBM platform and also globally from our external streaming platforms. Today's theme is all about open workflows, and in this session we'll have a number of short lightning talks. On this slide here you can see the ways that you can get in touch with us. If you haven't yet, please have a look at our website. We've got lots of information there about the program, abstracts for today's talks, and also information about each of our speakers if you'd like to know more. If you're on Twitter, we're very active on Twitter, so you can find us there. And if you're on Mattermost, we've got a general channel for general chit chat and also a channel specific for today's theme of OSR workflows.
Yeah, so as Cass said, we'll speak about open workflows today. And the idea is to speak about different works that people are doing that can help us build robust and reproducible pipelines for neuroimaging and neuroscience. So we'll have 5 talks and each will be 5 minutes long. We'll also then have a 20-minute Q&A, which will be live. And some speakers will be available for live Q&A in this particular time zone. And let's carry on to see how we'll approach the Q&A.
So if you're joining from the OHBM platform, you can use Q&A, the chat function during the talk. And then after, for the live Q&A, we invite you to join us on Crowdcast. If you're on Crowdcast, please use the question function and please upvote other questions if you want to see something answered particularly urgently. If you're on Mattermost, you can continue the discussion there and tag the speakers if you're able to. And also, we would love for you to fill out our feedback poll at the end of this session before you leave Crowdcast. This is so we can help understand what sessions are working for you, what formats you like, but also so we can give some feedback to our speakers on how well they've done with us. And finally, we would just like to remind you of the code of conduct. We expect you all to treat each other with kindness and respect. And when you registered for the meeting, you did agree to the code of conduct. So if you haven't yet had a chance, please familiarize yourself with that document. If you experience or witness any violations of the code of conduct, please do follow the reporting structure outlined in there.
So now it's my pleasure to introduce the speakers for today who will be giving the lightning talks. So firstly, we have Michael Joseph, who's going to speak about DMRI Prep, which is a robust and reproducible pipeline for diffusion MRI data pre-processing. Then we'll go over to Martin Greenyard, who will speak about Chamo, which is a tool for electromagnetic modeling of the head and sensitivity analysis. The third speaker will be Gaston Zanetti, and he'll speak about programming brain mapping hypotheses in NeuroLang. Fourth is Xu Chen, and she'll speak about RE-Brain, which is interactive clustering with spatial activation, which guarantees using all resolution in inference. Lastly, our last lightning talk for this session will be Pradeep Reddy Ramana, and he'll speak about conquering confounds and covariates in neuroscientific analyses with an open, high-quality library. So please enjoy all of these lightning talks, and we look forward to interacting with you on them.
Hi everyone, my name is Michael, and today I'll be sharing with you some work myself and others have done on DMRI Prep, a robust and reproducible pipeline for diffusion MRI data preprocessing. So I'll begin by referring back to a talk given by Jelle Verart at last year's ISMRM conference. So prior to this talk, Jelle polled the neuroimaging community to determine whether there was any consensus in preprocessing steps for diffusion data. So you can see the list of common steps over here. And the end goal is ultimately standardization. So if we want to compare the outcomes of different studies, having this standardization in processing methods will help enable this. And it was actually really encouraging to see that there is consensus that can be reached. So some steps you can see have the green light to proceed. Some have important caveats, and some require more evidence to demonstrate whether they actually make a difference in preprocessing. And what was also interesting is the ordering of steps in the pipeline may also needs to be carefully investigated. So this is where DMRI Prep comes in. And now you might be thinking there are so many different DMRI preprocessing workflows. What's going to make DMRI Prep any different? So here we have a table that compares some of the key features of DMRI Prep to other common workflows. And this isn't an exhaustive list by any means, but to summarize, the scope of DMRI Prep will be preprocessing. So we found that it's impossible to cover every endpoint, but what we do want is to provide the necessary outputs so the user can decide how they want to proceed with their data afterwards. So whether they want to build a connectome, perform chartography, or fit different diffusion models. And because the pipeline only accepts data in the BIDS format, it can be adapted to different acquisition protocols. It's community driven, and I'll come back to that at a later slide. It combines several different packages, and there's an increased level of testing, and all of it's publicly available on Circle CI. DMRI Prep falls under the umbrella of the NIPREPS organization, and here's a link to the GitHub repo where the code is stored. And so it takes on several of the same design philosophies. It's robust, easy to use, reproducible, and has a glass box architecture. And we also want to use the best tools and software to achieve this and continually update the pipeline when more improved methods become available. And so the pipeline is based on NiPipe, which allows you to create modular workflows of various preprocessing steps. And this can really help with the point I mentioned previously, how because we can plug and play different workflows and different orders, we can test how the ordering affects the end result. And also several features that were initially developed in FMI Prep have been abstracted out into separate projects, such as SMRI Prep, Night Workflows, and STC flows. This saves us from duplicating any previous efforts, and also eases the burden of maintaining the software since its components are split across different sources. And more importantly, STC flows allows us to access different susceptibility distortion correction methods, and we're not limited to top-up alone. So next I'll highlight some of the work done so far. DMRI Prep will inform the bid specs. So our group and others have posted issues in the bid spec and bids derivative spec. And through the process of developing DMRI Prep, we found some paths forward. One is storing the BVEX in a world coordinates TSV file format, and you can see what that looks like here. And another big development is being able to select the correct field maps for distortion correction, and this is something that we're currently working on. We also like the pipeline to estimate head motion correction, eddy currents, and susceptibility distortion correction in independent steps. And this will help enable better quality control. You can figure out what's going wrong with a particular step. The head motion eddy current correction estimation is something that's being actively worked on at the moment. And similar to FMI Prep, we will apply all of the necessary transformations in a single step. Also, DMRI Prep outputs subject-specific reports, and these reports help facilitate transparency for the pipeline. So they help the user understand, which pipeline steps are running and run things in a reproducible manner. If you saw at the beginning, there's textual summaries of the different T1s diffusion data that's been selected in all the steps. And here you can also see, as we go down, some of the quality control images, such as the distortion correction report and the masking report, right here. And so here's a list of contributors to the project so far. You can find more information on the importance of community-driven development on the NIPREP's website. But to summarize, growing a community helps with reporting bugs and improves the robustness of the pipeline on different acquisition protocols. Different users have their own unique expertise and may be better able to identify, propose, and peer review new features. So if you're interested, we welcome you to join the discussion on our GitHub issues and contribute to the pipeline roadmap. Thank you.
Hi, my name is Martin Greenhart. I'm a PhD student at the University of Liège in Belgium. I work at the CRC In Vivo Imaging Research Center. And today we'll talk about Chamo, which is a Python package that I've been working on for the past few months. Chamo is a tool dedicated to electromagnetic modeling of the head. So if you work with EEG, TDCS, MEG, or TMS, even if MEG and TMS aren't implemented yet, Chamo might be the tool you will need in the future. While developing Chamo, we decided that we wanted to make the step of generating subject-specific finite element model easier. So basically, we decided to cut off the steps of generating surfaces by allowing you to simply provide the segmented volume. So using the single line of code shown on this slide, you can actually go from the segmented volume on the left to the finite element model on the right. Chamo can be used to perform several analyses, such as forward problem solving for EEG, simulation of dipoles inside the brain, or even sensitivity analysis. Sensitivity analysis is actually the topic of my OHBM poster presentation at poster 1152. While developing Chamo, we also decided that we didn't want to reinvent the wheel by implementing custom solvers, so we decided to go with industrial-grade softwares such as Seagull and Gmesh for the mesh generation, and GetDP for the solving part. GetDP is a physical, flexible solver, so it will be very handy in the future as it will allow us to implement many other simulation pipelines. While using very powerful tools, we wanted you to have the full power in your hand. So we provide you with many settings, such as the mesh refinement parameters, the amount and the shape of the tissues in the form of the segmented volume. But you can also specify any number of sensors to place on the skin. So if you're working with HD EEG, you can use Chamo. But here, a key feature is that you can specify any amount of fields inside the head. So those fields can be referenced while specifying the tissue properties. This is very useful when trying to model the anisotropy of the right matter or the anisotropy of the skull, but it can also be used to model any other physical-based tissue properties by using scalar or tensor fields. Even if we wanted you to have full power, we wanted things to be as simple as possible. Here on the screen, you can see the full code used to generate the forward problem solution for EEG. As you can see, it takes only 10 lines of code, and 2 of them can even be removed and are only here for the sake of the example. So yeah, it will only take 8 lines of code to solve the forward EEG problem. The full code is available on GitHub, and actually the full code is documented, and we generated the documentation available also on GitHub using Sparks. So if you want to check that, feel free. We also provide Jupyter Notebooks examples. So if you want to test Chamo without developing a full project, you can just try it on toy examples. And everything is under GPL v3 license, so feel free to use it or extend it if you want for your research purpose. If you have any question or remark, you can get in touch with me by coming to my poster presentation at OHBM, so as I said, poster 1152, or by sending me an email or contacting me on Twitter and on GitHub. Thank you.
Hello, my name is Castronesis. I'm a first-year PhD student at the Parietal team in Rio, and today I will make a small presentation about the project we were working on together with Valentin Joven and Demian Wasserman. So I'm going to introduce Neuralink, and Neuralink is a probabilistic language based on datalog. And one of its main features, and which I'm going to emphasize today, is the ability to combine heterogeneous datasets to be able to perform efficient queries against this information. And we are going to use some meta-analysis cases just as an example of what we can do. So let's jump straight to the first example. I want to show some of the things that we can achieve. So here in the left, we have 4 rules that using the Neurosyn database are defining how its forward inference work. Let me say that we are working on a probabilistic solver, so the last rule will not be needed in the future. But for this presentation, I had to have the rule so I could show you the results. And with this, we can get all the voxels that are activated in studies with a specific term present on it. And in our case, we will base our example on search for the term auditory. And here on the right, you can see the actual results from Neurosyn using the term auditory. And this is the result that we get with running the query. And it's almost the same that the one that we get when using the Neurosyn web application. And it's known that meta-analysis tools sometimes offer results with low precision. For example, it can be seen in here that we are trying to obtain the activations related to the term auditory, but we obtain activations in the motor cortex that should then not occur in this case. And we thought that it would be interesting to be able to define regions as a priori in our queries to limit the activations to certain areas. So thanks to the fact that Neuralink is based on datalog and first-order logic, we can add that information easily. And here we are using the distro atlas. And the main idea behind this code is that we are modifying the rule that count the activations for a given term to add all the regions that we want to use as filters. Just that, it's a little complicated, but it's really easy. And this is the result for the query I should show. And of course, I'm not selecting the areas correctly. I mean, I should have choose different areas in this case to get better result. But one of the things I would like you to appreciate is that it's true that we get a much more precise result. You can see that the motor cortex is not activated anymore, but this procedure still depends on the selection of the areas by hand, and this can lead to errors like the one that I should make on purpose. And it would be great to have a way to say, okay, I want to get all the subregions that make up a specific region. And in our case, it will be the temporal lobe. So we can go a step further. And we are looking for a way to do exactly what ontologies do. And they are a formal way of organizing knowledge in a hierarchical way, with its own properties and constraints. And over the past few months, we have been working to enable Neuralink to include knowledge from ontologies. And we can then include rules that define all the subregions of a particular region, taking advantage of the hierarchical information in ontologies, and use it as a filter to obtain, in our case, all those related to the temporal lobe. And now we can see that the results are more precise than in the first example. And also, with this way, we avoid the errors of the second example by having to define every region by hand. And it's interesting to mention that we are using an ontology to define regions, but we could use it to obtain synonyms of a term, for example, and use them to retrieve information from Neurosyn without having to know them. For example, we can search for the synonyms of pain and use it to retrieve all the activated voxels from pain, nociceptive, and noxious. So let's refresh some of the ideas. Neuralink is a probabilistic language based on datalog plus minus. And datalog gives us a strong theoretical framework on which to develop Neuralink, drawing on more than 40 years of proven theories. Neuralink is an attempt to take a step in the direction of providing a unifying framework that allows researchers to represent their theories in a structured way. And of course, it's going to be released as an open source tool. And if you want to know more about the project, you can write me an email, or you can go to gitlab.com/Neuralink and get in touch with the rest of the team. And one more thing, we can also use the results obtained in our last example and apply reverse inference the same way Neurosin does, and obtain, in this case, the probabilities of a term given mentioned in a document given the selected activations. I select the first 10, but you can use all the Neurosin database. And our next step will be to try to use ontologies to filter the result based on cognitive process, disease, etc. And that's all. Thank you for your time. It's been a pleasure, and I will be waiting for your questions. Thank you.
Hello, today I'm going to introduce our new app, ReBrain, which can provide an interactive clustering with spatial activation guarantees using all resolutions inference. First of all, I'm going to give you a short introduction. The cluster inference approaches have become a standard in fMRI data analysis, but it has the problem of low spatial specificity. Finding a significant cluster using cluster inference means that there is at least one activated voxel inside the cluster, but we don't know exactly where the activations are. So if you would like to drill down into the cluster and localize the activations, you might encounter another problem of double dipping. This problem is related to selecting and testing the effect using the same dataset. Where our ReBrain app does not have these problems. It is based on a method called all resolutions inference, which provides a strong FWR control over all possible subsets of the brain. This app offers an interactive clustering method to generate clusters, and each generated cluster has the true discovery proportion above the pre-specified threshold. To use the app, you need to prepare a statistic image. That's the only compulsory thing you need to input. Here is the interface of the app. First, you need to input the data. I uploaded a ZMap. The acceptable file types include the ZMap, TMap, and the p-value image. If a TMap is used, you need to specify the degrees of freedom. If a PMAP is used, then you need to confirm the input p-values are two-sided. Next is to input the mask. The ReBrain can automatically generate the mask. If you like to upload your own mask, you can uncheck the box here and upload the file. You can also use the panels below here to double check the mask is correct or not. You also need to specify some analysis settings before running the analysis. Then you can click the Run Analysis button, and there will be a progress indicator here showing the progress of this analysis. For this dataset, I'm using the 3D dataset. It took around 2 minutes. Here are the initial results. The grayscale image here shows the maximum TDP each voxel can reach, with a brighter color for a higher TDP and a darker color for a lower TDP. You can use the download button here to download the gradient map. Before going to the interactive analysis, you need to first create the clusters. There are two ways to do that. The first one is the traditional way to apply a single cluster forming threshold to the entire brain to form the super threshold clusters. And the second way is to use the TDP threshold, and each created cluster has the TDP above this given threshold here. Then you can click the To Form Clusters button, and the clusters are generated. Here, different colors represent different clusters. And if you click a cluster, then the corresponding TDP bound will be shown here using the slider bar. You can also download the cluster image by pressing the download button. Let's move on to the interactive results here. You can change the size of the created clusters. Increasing the cluster size leads to a reduced TDP, and decreasing the cluster size leads to a higher TDP. If you click the cluster here, like if you choose the red cluster here, the corresponding cluster information is also shown here in the cluster table. It's also chosen in the cluster table underneath. There are two buttons here. If you click the increase size button, then you will increase the size of cluster 1. Here the size is dramatically increased because cluster 1 and 2 merge and the TDP drop to around half. You can also see the merging part here in the image. Here two clusters have the same color. And if you click the reducing size button, then you will see the size is reduced and the TDP goes up as expected. You can do this for all these clusters, and then click the download button to save the interactive cluster map. And the RePrep app is currently on its beta version, but it will soon be available on GitHub. So you are very welcome to join us and try your own dataset using this app. Thank you.
All right. Thanks everyone for coming. I love to present in the Open Science Room. Today, I would like to quickly talk about how we can conquer confounds and covariates in machine learning and neuroscientific analyses. So essentially, if you ask me what are confounds, I would try to go with the statistical definition, which is basically any variable z that influences both a dependent variable y and an independent variable x, causing a spurious association between x and y, right? So we say x and y are confounded by z if z causally influences both x and y, right? So you want to try to remove the effects of z so you can actually estimate the effect of x and y, right? So simple neuroimaging example is x is often imaging features, y is patient diagnosis, z are age and gender, right? There's many more variations of these confounds and covariates as listed here, including ICV, site, education, income, lifestyle, etc., right? So nowadays, given how large and multi-site data sets are, these are quite common, and handling some variation of these confounds is a necessity to do anything non-trivial in our analysis. So the problem is, well, the common approach to these nowadays is that, has been for some time, is that people pick some potential confounding variables, whether or not they're actually confounding or not, we don't know. Regress them out and pretend everything is fine. But it's a problem because we don't even have a clear accepted definition of what constitutes a confound and whether we can actually verify it is indeed a confound. It is often assumed they are, and the age is in aging applications, but may not be everywhere else, you know. But we don't have a clear metric or ways to estimate the level of confounding, right? And whether we should be confounding it or not is another open question. How and whether to tell whether we did it right or not, there is no clear protocol or framework, right? And to assess whether the method actually did the right thing in a given analysis, or whether we introduced new or unwanted bias is actually a problem, right? So in order to try address these open challenges, I built this confounds library, in fact, to help actually offer deconfounding features in NeuroPredict, but I believe this is also very useful and important for the community at large. So goal is to build an open source, high quality, well-tested library so people can depend on it. Makes it easy to visualize and establish the presence of confounds, quantifying confound to target relationships, and solutions to handle them, and also with related methods and libraries to actually analyze the effects of different confounding methods, especially to check whether they worked or if they introduced new or unwanted biases, right, which is important, not often done. So just to give you a quick overview of the landscape of various methods in the confounding world. Example, this is all, you may have seen these methods often used in papers, and some variation of them. Each of them have different variations. For example, you can regress them out, regress variables out with a linear or non-linear model. Scaling can be done locally or globally, or harmonization can be achieved with a normalization in different ways, or using surveyed wave analyses or combat. Or you could also just subsample or resample the data set to minimize the confound to target correlations as well, right? So in order to try offer solutions to this landscape in terms of implemented methods, confounds library mirrors the structure, so to say. You can see various classes trying to offer the functionality as listed in the confounding landscape, right? So by starting from base the confound, so to say, it has many great features, such as they all act as cycle-learn estimators, highly modularized, means easily extensible and testable, and development will be test-driven, focused on usability. And the boxes highlighted in green are already implemented and usable. Go check out the documentation. And I really need your help to implement the rest, test and document them. So I invite you to contribute to this very important, very useful and a great cause. The URL is here. I'll be working on this at the OHBM hackathon, primarily focusing on implementing combat, but I would take any help related to this. Thank you so much.